In this video we're going to consider what happens when we have a sector of a circle with an angle theta measured in radians, and what we're going to do is let theta tend to 0 or become extremely small. And what we're going to do is work out some expressions for sine theta, cos theta and tan theta if theta tends to 0. So this is a follow-up to the previous video when we did a demonstration that showed that sine theta in rads is approximately the same size as theta in rads, and likewise that tan theta was approximately theta as well. But that video was merely a demonstration, it wasn't a proof. This is an actual very simple proof that you can use if you need to show the same result. So what we've got is a sector, radius r, angle theta in radians. And what I'm going to do is I'm going to create, by drawing a perpendicular dotted line straight down here, a right angle triangle. And I'm going to use on this right angle triangle a bit of right angle trigonometry, SOHCAHTOA work. There's the angle theta, that's the opposite side, that's the adjacent side, and that's the hypotenuse. And for that right angle triangle, I'm going to write that the sine of theta for that right angle triangle is going to be equal to the opposite over the hypotenuse, which is the opposite, divided by, now in this case the hypotenuse, I could call it h, but that is actually the radius of the sector, so I'm going to write it as O over R, like so. I'm also, whilst I'm at it, going to do the same thing for the tan theta one, because sine and tan theta are the easy ones to prove. The cos theta one, as I showed you in the previous video from the demonstration, is a little bit harder, so we'll do that a slightly different way. So from the picture, tan theta is going to be opposite, that's the dotted line, divided by the adjacent, well that's from there to there, that's not the radius, so I'll call it still the adjacent. So we've got those two expressions for the right angle triangle that I've just constructed. Now what I'm going to do is I'm going to say, as theta now tends to 0, it becomes much smaller. So let's actually, I'm going to redraw the picture now with the sector having a much smaller angle, and I'll really make it quite small just to demonstrate what's going on. So there's the sector now, theta's tending towards 0, it's becoming much smaller, and I'm going to drop the vertical again to make a right angle triangle. Again, that's the radius of the sector. Now if you think about this, if I now say as theta tends to 0, let's see what sine theta tends towards. Sine theta will tend towards, now we know, if I just pull this back down again, it was the opposite side divided by the radius when it's a general sector. So in this particular case, what do we get? The opposite side. Well, the opposite side is that there, that's the adjacent, and that was the hypotenuse. The opposite side is the dotted line. Now as you can see, because the angles become so small, that dotted line is getting much closer to being the same length as the arc across there. So those two distances, the dotted line and the arc, are extremely similar. And the smaller that theta gets, the more close the dotted line becomes the arc of that sector. The way I've drawn this, that arc looks a bit more curved than it should be. It should be a lot shallower than that. So in that case, the dotted line and the arc would be extremely similar in length. So it tends towards being the arc. Because the dotted line is very close to the arc, we can say that sine theta tends to be, instead of the opposite side over r, I'm going to say it's very close to being the arc divided by r. Now you should know from your basic work on radians and s equals r theta work that the arc length is the same as s equals r theta, so it's the same as r theta divided by r. So arc is r theta, r on the bottom line. So you get that sine theta now, this is what we need to remember. Sine theta tends towards, this is a fraction, the radius and the radius will cancel, so sine theta tends towards theta. And that is the result that we saw from the demonstration in the previous video. So for theta in radians, when theta is very small, sine theta tends towards being theta. In other words, these two things are equivalent for small angles theta in radians. Let's do a similar sort of thing for cos of theta, for tan of theta, I apologise, tan theta tends towards, if I go back here, tan theta was O over A. So looking at what happens here in this situation where theta is becoming very small, opposite is going to be the equivalent to the arc divided by the adjacent. Now this is slightly different this time. This here is the adjacent, and the adjacent side, as you can see in the first picture, the adjacent was much smaller than the radius, which would have been from there to there. But the adjacent is from there to there, so it's much smaller. You can quite clearly see it's smaller. But with the way I've drawn it now, when theta tends to become nothing, the adjacent is near as damn it the same length as the entire radius of the sector. So what we get is, as theta tends to naught, tan theta tends towards, instead of O over A, O is equivalent near as damn it to the arc, and the adjacent is near as damn it equivalent to the radius. So what we get is that this tends towards the arc is r theta from s equals r theta over the radius. And again we get the same cancelling taking place for this fraction. So we end up with tan theta tending towards theta. So what we can see from this, that as theta tends to 0, in other words for very small angles of theta in radians, tan theta is approximately the same size as theta. It tends towards being the same as theta. So those two results are very important, and you need to be able to reproduce them and use them. We normally write this as sine theta equals theta and tan theta equals theta for small angles theta in radians. Okay, now what about cos theta? Well, cos theta works in a slightly different way, and what we're going to do is make use of this identity which we should know from our double angle identity trig work. Cos of 2x is the same as 1 minus 2 sine squared x. That's one of the versions of cos double angle that you should be aware of. Now in this particular case, what I'm trying to do, I know what sine theta is, I know what tan theta is, I'm trying to work out what cos of theta is. So cos of theta is going to be equal to, well okay, so what I'm going to say is cos of 2x is 1 minus 2 sine squared single x. So cos of theta is 1 minus 2 sine squared, and instead of, well, the 2x becomes 1x, so the theta becomes half theta. So we get that. So we get that cos of theta, let me move this up, cos of theta is going to be equal to, now what I'm going to do is say to you, as theta tends to naught, cos of theta is going to tend towards, okay, so what we get is 1 minus 2 lots of, and it's sine squared of theta over 2. Well, that means sine of theta over 2 all squared. Well, we already know that sine of theta tends towards theta. So sine of theta over 2 tends towards theta over 2. And then you square it. So you're going to get theta over 2, and you need to square it. So we end up with cos of theta tending towards 1 minus, if you square theta over 2, you get theta squared over 4. Then you double it. The 2 and the 4 cancel, so you get theta squared over 2. And that, as you'll see, is the expression that we showed in the previous demonstration video. And we normally write it as cos of theta is equal to 1 minus theta squared over 2 when theta is in radians and theta is small. Let me write it like that. So there you go. So there are the 3 different trig expressions you need to know for small angles theta in radians.